Welcome to the first Dlubal webinar in 2026. On behalf of the entire Dlubal team, I wish you a successful and happy new year. Now, enjoy structural analysis with our software. The topic of today's webinar is nonlinear time history analysis in Rfem 6 and RSTAB 9. Quite new feature. Just enjoying the webinar. Let me introduce myself and my colleagues. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will answer your questions together with Victor Hidalgo. The presentation will be done by Thomas Eichner. He works in the Dlubal support team, and he and also Victor are the responsible persons for the development of the dynamic add-ons. And I wish you that you enjoy the webinar. I say some words how you can ask questions, at least for the attendees who participate the first time. At first I switch off my webcam that you can see the full screen. Just press the button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. Okay, that's for the moment all from my side. I hand over to Thomas. Thomas, you can start.
So, thank you very much for your lovely introduction, Andreas. And also a happy new year from my side. I hope you went into the next year, into this year, with a big bang or something like that. At least I'm gonna try to do the same, since today we're gonna look at a very interesting topic. And I also prepared a bang for you today, and we're gonna simulate one. It's gonna be a pendulum impact, simulation, but let's not jump too far for now. We're gonna start quite easy, and it's gonna be about the nonlinear time history analysis. So let's jump right away into today's topics, which are quite some. We will start with a short overview on the features of the dynamic add-ons in Rfem 6 and RSTAB 9. It's going to be followed by 3 steps at once. The introduction on how to use the nonlinear time history analysis within the program. Also, it's going to be directly demonstrated while considering nonlinearities in a time history analysis, followed by another example with failing elements. And then we're going to go right at this bang moment, which will be this pendulum impact test. We're going to investigate on this pendulum impact simulation with first a simple surface model. We're going to expand the surface model with a solid model. And in the end, I'm just going to give a short outlook on how you could proceed with a more detailed impact model. However, I didn't finish that impact model, so please feel free maybe to advance it yourself. In the next step, we'll also go in the direction of the so-called the performance-based design. We're gonna also see it on the right-hand side of this slide. We're gonna see acceptance criteria given in colors and everything. This is also then, the introduction for some other new advancement. I'm not gonna relate it to the nonlinear time history in this webinar, but we also introduced new nonlinear hinges according to the ASCE 4170 for reinforced concrete beams, which are also shear force dependent. In the end, we will have some concluding remarks. This is like always just some tips from myself. So let's go right away with the introduction and overview on our features. Well, we have the modal analysis add-on, which gives you the opportunity to investigate on modal properties of our systems. For example, the modal frequencies or the modal eigenshapes and modal masses in general, all that stuff. Followed up, there's the response spectrum analysis add-on. Well, it just creates like states of the system according to an eigenshape, and the states have internal forces and deformations, and we will get these results for each shape, and according to the standard they will be combined, for example with a 100% 30% rule, CQC rule, or SRSS rule. Well, the 130 is more for the directions, but so in the end, we will get an envelope of results, of internal force results, which can be used further for the design. Then we will go into the first nonlinear analysis, which is the pushover analysis. First, it looks quite complex, but the theory behind it is, well, quite simple. It's two parts. The first part is just we will get the force deformation curve of the system under horizontal load. So we just, the analysis is quite simple. We just press the system from one side until it either reaches an wanted point or it breaks. And with that information, we just have it displayed in a simple graph, in a force deformation graph. And since we are engineers and well-trained engineers, we can get a lot of knowledge out of that graph and use it further. So that's a perfect tool for interpreting your structure. The second part is, well, it also puts the demand into place in form of the response spectrum, and this is related to a single degree of freedom system, and quite handsome that we already made the pushover analysis, which gave us this single degree of system behavior of our multi-degree of system behavior with some transformation, but we got that out of it, so we can compare demand against capacity, and then we know where we are at. And since we then know where we are at, we can also investigate on what damage is estimated to be there and where it could be. So then we can decide where we should look to reinforce single columns or whatsoever, which we would have expected the damage to be at. And in the end, there's the time history analysis, which, it can be split in the linear one and the nonlinear one. The linear one is already treated in some webinars. It's more like about the vibration investigations, for example, of human-induced vibrations or machine-induced vibrations, where the nonlinearities are not that impactful. But at, let's say, pendulum impact or explosions, or at performance-based design, there we will need to take damage into account, or geometric nonlinearities, or whatever nonlinearity there could be. So there we would also need the more complex one, the nonlinear time history analysis. And this will be the topic of today. It's like in my opinion, the most exact solution within structural dynamics, and therefore it's also the most complex one in structural dynamics, in civil engineering in general, in my opinion. So it's kind of the king's disciple. But we're gonna have a look at that today. So I'm quite happy to show it to you. So let's go on. That's quite a step too far. We're gonna start quite simple. Let's go within our program. The first thing is we're just gonna validate that simple nonlinearities are considered within our new analysis type. Therefore, I prepared a simple model. It's just a column. It's a reinforced column, concrete column with, I think, 30 times 30 centimeters. Yes. 5 meters long. It's fixed at the bottom, and also we have two cables, one at each side. And this is what we want to verify. For the masses, we have the self-weight of the system as well as one kilonewton force on top. That will be our mass matrix. And for the loading, we have 100 kilonewton, which we will apply with a sinus, I think, a simple sinus function of 0.5 times t. So in 10 seconds, it will just go 1 times to the one side and 1 times to the other side. What we want to verify is that the cables will fail if they are under pressure. And that's the investigation we will go for first. For the investigation, I also want to show you what is needed for this nonlinear time history investigations. And that's quite some present, I would say, since let's go for the base data. For our add-ons, there's nothing selected yet. And if we want to go for a time history analysis, we don't care if it's nonlinear or linear. We're just going to press the time history analysis button. Well, the modal analysis is always needed as soon as you want to do anything with dynamics in the program. But yeah, so what you can see here, we don't have another add-on implemented. We also didn't change the price of this time history analysis add-on, which means if you already purchased the time history analysis previously, you're just gifted with the nonlinear solver. Also, if you would buy it now, there's no change in the price for it. So feel free to get it as long as it is like that, because that's quite a gift, I would say. Okay, let's go and go out of it. We activated the time history analysis. And now we will go for the first step. We will go for our load cases. So there are the same possibilities as in the linear time history analysis. We can go for load cases or load combinations of the type time history. So let's go first with a load case of type time history. So I'm going to copy this load case too. So I will also have the loading within the load case. Then we will change it to a time history time diagram. Let's name that load case time history analysis time diagram. That's quite cool. And okay, so there it is. We can select that. We have our masses already selected here, and we can go for our time diagrams. Well, that's quite simple. We will go for a function time diagram of, well, what's that? It's sinus 0.5 times t. Always consider only using points here and not commatas. Commatas are used for other functionalities in this function. But yeah, we will go for 15 seconds here. So we have all there, I think, but we will only calculate until 13. That will be enough. Whatever. The time diagram max limit will be 15 here. So we have two, well, both here, one in each direction, just for the verification then. Okay, there we have it. This single force load case time history analysis time diagram. It's a long name. Let's delete that. Okay, now we will go for our time history analysis settings. So maybe just one benefit here. Let's set the linear one first. So let's see, we have the linear with 13 seconds. We have a time step of 0.1 seconds, which is saved. And the saved time step, we will split it even further by 1000 steps. Since, well, we also have cables in the systems. I think I have the basic division of members is 10. So we have 10 divisions for members, and cables make it quite, let's say, unstable. So we will use quite some time steps in that case. For the calculation parameters, well, I don't really care about the rest. We will only go for the x direction here, and that's all. We can stay with the consistent matrix, even though it wouldn't make any difference with the diagonal in that case. Then we will go for the damping. The damping, well, I just selected. There's not too much physical meaning behind it, but well, I can try to get a physical meaning out of it. Let's say we have a frequency of 100 Hertz. I'm not sure if the system has an eigenfrequency of 100 Hertz. I have no clue, but let's assume it has a frequency of 100 Hertz, which would dominate the structure's response. So I want to dampen this frequency by 10%. It's quite some high damping, I would say, but yeah, that's the thing I think about behind inputting that value. Okay, for the beta damping, I try to avoid it, to be honest, since it often causes convergence issues currently. So also maybe a tip for you, if you get with a time history analysis, if you, well, with a nonlinear one. In the linear, it's no problem, but with the nonlinear one, try to get the beta value to 0 and try it again, and then you can investigate the results, and then you can adjust it. That's always a first support stuff I do at customer models. Okay, but that's it. It's already done here. What we will do next is we want to do a nonlinear time history. That's all we are talking about today. And well, it's quite simple. We have the linear settings done. We just copy it and we just change the solver to the nonlinear implicit Newmark one. And it's finished. So that's quite forward and quite simple. If you have some systems to test it, just try it out. But also maybe try increase the time steps as well and play with the beta damping as well, please. That will help a lot. Okay. Now we will just accept it, and I will just directly select this nonlinear solver for this load case. For the next load case, I wanna go with a time history analysis of accelegrams. So with that, also the nonlinear solver, also the same masses, we can select an accelegram from, let's take it from our library, like anything there, Chile, I don't know, what's that? Let's go for some 16 seconds. That's okay. Let's go for Valparaiso aftershock. Okay, for the Chile earthquake. It's quite small. That's okay. Just gonna take it. Just to have some accelegram time history as well in that calculation. Okay, and so with that we have all possibilities of the load case time history analysis. Now we also go for load combination time history analysis, and that's like my favorite. I'm almost only working with those load combination time history analysis for time diagrams. They are not available for accelegrams, but for time diagrams, I almost always take load combinations. The thing is, we can just do more stuff with it. Right, the load cases are okay, but we can only assign one loading with one time diagram. In the load combinations, we can do the same, but we can also add another loading with another time diagram. So yes, in the end, this is the same as the load case time diagram time history. And well, that's like the same setting right here. We just have one time diagram and one load case here assigned. We could also go for this direct. We could use that, and it's automatically filled with the right time diagram that is used in this load case. But we don't need that. Okay, so here we will go for the differentiation. We will make one for the linear time history analysis, and we will also go for one for the nonlinear one. So let's call it COTHA time diagram. Linear. And the second one will be the same but nonlinear. and we change the solver there. And well, quite forward, that's done. Let's just calculate it. And since it's gonna take 3 minutes and I really want to show you some stuff today, I want to just first show you we have 4 time histories. They are all done at the same time, calculated at different cores. That's a difference to Rfem 5, where it would all need to be calculated one after each other. So it's quite a ton of faster than the other one variant. However, I really don't want to wait this long. Let's just switch to my prepared results model. I also prepared all the results for our further models since it's needed. Let's go for the results of this time history. We will start with our load combinations linear one. For your information, the best ways to investigate on the results is either using these calculation diagrams, which I prepared here already. For example, we can see the maximum deformation in the graph. Just select the time history analysis here, so you can have the result type time here. Let's go and create one new for, let's go for the load case 3. No, we want to have the linear load combination, just as an example for creating those time diagram, those result calculation diagrams. We will go for members, internal forces, normal force of this cable. So the thing is, we wanted to see if it's failing. And since we are in the linear time history analysis, we see it's not failing. It's first gonna take like tension force, and then it's gonna take like pressure. So the pressure is just wrong. It should fail here, right? And that's the thing. But we will go for a different investigation now. Don't need to change this. No, don't need to save this. Let's go for our calculation diagram monitor, which is right there. That's some cool thing. We have the same diagram. We have the possibility to show one calculation diagram while we are in the program. And also, if we now start the animation, we can see it right there. It's also going to show us where we are at. And there you also see like the normal force of this cable right now. Well, it's just gonna hold it completely with tension and pressure, and that's wrong. So now for verification, quite simple. I'm gonna select the load combination 2, and there we have it. There's only tension force, and it's failing at the pressured region. So let's start the animation on that. We also see it's running quite better here. We also have way different, way bigger deformations. Well, not way bigger. I mean, in the end, it's still fixed. It's still a column here, but yeah. That for validation there. Validation is done already. We can also go for a short second. Let's see at the load case time history analysis accelerogram. We also see here there's only tension forces, never negative normal forces in the cable. So confirmed again. One more thing I want to show you. Let's go for the load combination 2. This is the normal force for the left cable, and this is the normal force for the right cable. We see it's working as estimated. Also, we have another thing, and it's called the group diagram, where we can combine now this diagram 6 with the diagram 7. So the normal force of the left cable with the normal force of the right cable. And that's quite handsome. Okay, so first investigation done. First non-linearity is successfully confirmed. Let's go for the next confirmation. And that's gonna be some failing supports. Here you can see I just prepared a model which has fixed supports, but it has failing supports if the force is pulling up. So if this P set is negative, then the support fails. quite straightforward here, and we already see the results of the linear time history with the results of the support force at this left corner here. We see the loading. Well, there's just one fail I did. I have one loading that's a bit different. Or no, I have two loadings that are a bit different, but it doesn't make big of a difference. It just is a bit not anti-metric because of that. Let's see how it's going. I'm gonna start the animation, and we can see now the supports always take support forces in both directions, as also stated in this diagram. What I did here is I just used time diagrams. I did quite some theory crafting, I would say, on this model, since I did use, let's see, okay, it's not on that model. What I did is I just used the first mode. So the first mode is of the modal analysis is used here. It's the 15.236 rad per second. So it's the not the natural frequency. Let's see, it's the omega of the first mode of the linear system. I used it here and just applied the loading. I just applied the masses in x direction. That's what this time history does for linear and for nonlinear. So the same I did for the nonlinear time history analysis. So let's see here. As we see, it's just like opening up. I also included some damping. So we see it's kind of at its, it's just like rising. It's always starting up, and then the damping comes into place, and it stops rising. I'm just missing a word for that, but that's no problem. I think you know what I mean there. So let's switch to the nonlinear time history, and we would estimate, there we see it. We would estimate these forces only to be positive. Let's go and see it. Yeah, and there it is, only in one direction. Here it's shifting. Here it's shifting. Okay, we're gonna increase this by 100, the deformations, to see quite better. Now we see, it's lifting up, and it's going down again, and then this side is lifting up. So the next nonlinearity is confirmed by that investigation. And now we can continue with the, let's call it good stuff. For the good stuff, we have the pendulum impact analysis, or simulation in this case. Now I want to go, let's see here. Okay, perfect. Let's see first about the system. What we have there, this should be, well, a glass surface. It's just one surface. It's a chemically strength glass, 8 millimeters of thickness. We have 1 meter height, and let's see here, 1 meter height and 70 centimeter length. And we have it like supported on top and the bottom with line supports. Now what we want to do is we want to have this bang. We want to have this impact. Let's see what it means. That's what we're gonna do. So that number 3 here, that's our surface. Then this wrong model in this one. So you see this system here, that will be our impact model. Let's go back for the presentation. So it's gonna be this stuff. And the real procedure is we would have it hang up here, lift it up, and then it would be let loose and it would bang against the surface. It would just bang and then it would go back again. All right, so there it wouldn't go there and then go there again and again. That's not what we want to simulate. It would just bang once, get away from it, and then it's away. That's what we want to simulate. So for the energy, we will see this in the results in the end. However, what we can see here from is we will go with an impact energy of 100 Newton meters. Okay, so what we want to have is at the impact, we want to transfer 100 Newton meter energy. So how can we achieve that? Well, we know we have this impact system which has 50 kilograms. That's the mass of the impact of this. I think it's a tire which normally is weighted with a medicine ball, something like that. So that's the system, and it has 50 kilograms, and it has roughly a stiffness of 400 kilonewton per meter. That's also gonna be in our stiffness there. So now we know the energy of 100 Newton meter. With that, the law of conservation of energy, together with the impulse theorem, we can calculate a force F. I did let out some intermediate steps, because the force F can be derived from the impulse change over time. So there are some formulas missing in between, but that's what's behind these formulas. So the time which we do take, we just pick it. We decided it's 0.001 seconds. And with this 0.001 seconds and this derived formula, we can have the mass that is needed to achieve, well, this energy. And we also know for an impact energy of 100 Newton meters and a mass of 50 kilograms, we know that the velocity at the impact of this tire would be 2 meters per second. This is going to be something we will validate within the results. So this velocity at the impact will be 2 meters per second. We're going to remember that. So to achieve this 2 meters per second at the impact, we will need to put a force of 100 kilonewton over a period of 0.001 seconds. With all that information, we can also calculate what distance it needs to be at that energy or at that velocity, and it will be 1 millimeters. So we will need to not have contact between those two systems for 1 millimeter while it's accelerating. Okay, and now we will take all this information and go into our model. So we have a unit load case. So later on we will modify it. This is just a unit load case with 1. It doesn't matter too much. You could also put this 100 kilonewton here or later in the factor. That doesn't matter, but it's a unit load case. Then we have the system of our tire, in this case, a really simple system. It's just a spring, and the spring has a stiffness of 400 kilonewton per meter. It has no mass itself. We defined the 50 kilogram itself in our mass load case on one side. And we have a partial activity, which means we can insert also a slippage of 1 millimeter. So that's the time we need, or the distance we need to accelerate to this 2 meters per second. And we also have a spring ineffectiveness in the other direction. So it hits, goes with the structure. Let's go out here. It hits it, goes with the structure there, and if it goes back and is not linked anymore, then it's ineffective. So that's how we make sure that it goes away after the impact. Okay, and now, well, that's quite forward, and that's it already. Now we can go for the results and investigate on, well, I already calculated it. Maybe we can go also for our time history analysis settings. So as I said, we have the masses defined in our mass load case 2. We have our unit load case with 1 kilonewton. Now we will go for a load combination where we defined, well, they are all the same. The only difference will be the time history analysis solver. So we can look at the assignment. What we did there is we have our unit load case, which has 1 kilonewton, and we assigned it with our Pendelschlag. It's a pendulum impact in German. There we have the 0.01 seconds, and we have this multiplier with 100. So that's what we do there. Okay, done with that. We can go and look at our time history settings. In this case, I always looked at all the time steps and splits are the same, but we don't need that precise ones for the linear one. But however, I just picked it the same. So now we have times that we will calculate 0.15 seconds long. I think that's different. Yeah, I did it for the nonlinear time history. I did it longer. I will show you why. We have a safe time step of 0.001 seconds, and we will further split it by 10 to have more calculation time steps. For the calculation parameters, it's a diagonal matrix with all components. Damping, I think we don't have any damping in this case. I didn't go for damping here. We could also try to estimate some damping, but I didn't try for it yet. So okay, but with that we are done already. Well, the modal one, we can just ignore it. We won't look at that. It's gonna be the same results as the new mug. It just needs a modal analysis first. Let's go for the results now. We will see the new mug one, and we will see let's see. This is the UX of node 6. Node 6 is this one here. Yeah, but let's just start the animation. I will just override it a bit so we can see more. Let's factor it with 5 and start animation here. Now we see it's gonna make the bang, and then it's gonna rotate a bit. The thing with the linear one is our spring non-linearities are neglected. That would mean it would still be connected in the end, and it would shift sinusoidal, it wouldn't be split after the impact. So this would just go up and then down again. For the velocity, maybe let's go for our time diagrams. There we see it. We see here our almost 2 meters per second, which is a bit off since, well, we also don't have this 1 millimeter slippage. It doesn't have too much influence, to be honest, but yeah, it's just a little bit off because of that. Also, maybe a bit more precise time step would also help a bit. But what we see here, we go and there it should stop. We know it this negative way that shouldn't occur. That means the ball comes back again, kind of. And that shouldn't be. It should be constant at here. So it's not connected. This means it's connected with the surface and it's gonna be pulled back by the surface. That's not wanted. Now we're gonna look at our nonlinear time history. And there we see some difference. It's not gonna go this sinusoidal way. I mean, okay, it's 0.5 seconds longer calculated, but also we see here some change. It's not linear, right? And if you change it for the nonlinear one, we see it's just linear at that point. So the deformation of that right-hand side point, it's just rising, means this pendulum kind of is just going further and further away with the same velocity. We can also try to get this other point on the other side. Let's go for this. That's the point on the surface. There we see how that is going, right? It's not going further away, but it's like here, it's just like vibrating in the end, the surface alone. We can also try to get it on the non-linear time history. Yeah, there, that point, well, it's connected. It's not right, to be honest. It's quite hard to interpret in that short time. Okay, let's stay with the nonlinear one. And with the nonlinear one, we can also, I will stay inside that point. Let's go for node 6. Let's go for the velocities in that point. And we will go for ux, and there we will see this 1.99. It's quite close to 2.0. 2.0 meters per second. That means our first theory was confirmed. We have this impact energy of 100 Newton per meter, since we have this 2 meters per second. And what we also see, we see this constant velocity in the end. That means at that point, they are not together anymore, and like the system on the right hand side, the pendulum is just going to travel further and further to the right. Let's look at it also. Let's do it a bit bigger. There we see it. Now it's kind of together. The stiffness plays a bit of a role in the difference here, and then we see it. It's going to move. And yeah, it's quite working fine. We can also like change the animation speed here a bit, so it's a bit too fast. Well, now it's not fast enough. Let's go here. Yeah, that's a bit better. There we see the stiffness just has some impact here for the relative between those. Now it's gonna shift and just move away. So that's confirmed again. So let's jump for the next model. It's the same model, but it's cooler. Now on that model, what we did is we included also some, in that case, we have double glass surfaces on both sides, and in the middle we have like air as a solid. So this is the solid model of this structure. It did need some mesh refinements here, and it also did I did some iterations for getting the results as they are now. We will just go straight forward, and we will go for the non-linear time history analysis, and we will just go again for our velocities on the point. And we will have to quite the same. You see, well, in that case, it's again only calculate till 0.1 seconds, not till 0.15, but we see this, how it's not changing at that point anyway. So also that is working quite fine. We have also this 1.99 meters per second, so that's quite nice. Let's go for the animation in that case. We also see how it's like moving the whole body here. This whole solid model is going to be moved and it's going to go back. We see this behavior is a bit different to the surface model, especially since this is way more stiff. Okay, and it's just for presenting you. It's quite a powerful analysis type. What I want to say here anyway is we do not have everything in our automatic tests. And it's something we did here. We have warnings implemented. Just because there's a warning, we didn't want to like block features. Let's say, for example, surface contacts with whatever nonlinearity. We don't have an automatic test for that yet. So we just want to hint out what is within our automatic tests. So whenever there's something not tested, you will find such a message here. But it doesn't mean that it is not working. it just means please investigate it on its plausibility, because that's something, I mean, it should be clear in general that one should like test the program on its plausibility, but with that we have tons and tons of features, and it really gets customers to use anything with anything, and that's, I think it's sometimes dangerous, and for some customers I want to have this warning to be displayed. That's just to hint out, don't trust a program blindly, right? I hope most of you understand that. Right, so for that we also implemented where the feature untested stuff is. For example, here we have, I think, the surfaces, or the most simple one is the solid, of course, because we didn't test the solid yet in an automatic test. We just tested it on its plausibility like that. Also, for example, there are overall warnings, which, for example, are, imagine you are trying to use a torsional warping 7th degree of freedom with nonlinear time history. Nope, that's not tested yet. I'm not sure when it's gonna be tested, because that would be some new studies needed, I would say. So there are a lot of stuff you can combine, but please investigate them carefully. So, and now for the last of this pendulum impact stuff. I didn't get this to calculate quite far. Yeah, it's still getting my assert here there for the changing. And that's something where I tried myself on modeling this contact more exact. In this case, in this model I tried it with our rigid link, which is a link between two lines. There's another test where I tried it with like single links at each node. It worked a bit better. Well, to be honest, I don't know if it was better. I just investigated it in more detail and with more complex mesh settings and time settings, but that was an iterative process. What I can say is like 2 elements, it doesn't seem enough in between those. And also the time settings seemed not enough for this detailing. Okay, so I hope this was a fun bang into this year. And now let's go further with our performance-based design. Let's see, do I have another? No, that's not. That's jump too far. Let's go for that here. We will go now for, I want to show it in RSTAB 9. Since in RSTAB 9 we also have something different there. We have a different solver than in Rfem 6. So in RSTAB 9 there's this nonlinear explicit one instead of the nonlinear implicit one. It's 2 solvers, one is geometrically linear and one is with large deformations. And as a hint, even though it's called nonlinear explicit, it has some benefits, well, within the solver which relate to the implicit Newmark one. So it's not purely a nonlinear explicit one, but that information is not completely clear for me. It's gonna be in the handbook, and yeah, please feel free to look at that in the handbook. The thing what that helps in the end is it will help with where other solvers would get unstable, which I will show you right here. It's gonna help. So for that model, just for your information, this is related to the performance-based design topic, where we're gonna try to do nonlinear time history analysis of for earthquakes mostly. And within that region, there maybe just as information, I didn't use it here, but you can always use structure modifications in any case to like modify stiffnesses and everything to get from, I don't know, characteristic values to estimated or mean values or to correct values and so on. You can also use it for your modal analysis. So this feature is completely there for you. Then for this feature, there's also this hinges. There's nonlinear hinges in this case. In that case, I just used the FEMA 356. Later on, I'm going to show you the new ones, this ASCE for reinforced concrete beams, according to 4117. In this model, we use the FEMA hinges. We also see this acceptance criteria and so on. You can also define everything user-defined if you want to. And yeah, also the coloring there. Let's see, we will just go for a nonlinear time history. Well, that's the model where I did some tests, let's say. What I did there is I did a modal analysis, I did a response spectrum analysis, and I got this information of the modes. So I did a nonlinear time history in the end where I said 0.845 times this acceleration of the first mode. I will apply with this frequency of the first mode, and then I will also use this this mode with 9.3% with that acceleration and that period and so on. Let's look at that, what I mean here. Here you can see it. I used the self-weight in X. I said it shall be taken with the frequency of the first mode. Is it the first mode? No, this is the first mode. Well, the first X mode, and I scaled it with the effective modal mass of that mode and the acceleration of that mode. So that was my try to compare those analyses with each other. Wasn't that successful, to be honest, and I will investigate further for sure. So, but that's the analysis we do here. We have like 2 frequencies in one direction, 2 frequencies in the other directions, and we will just go for the comparison. Think for the RSA there's a Q factor of 1.5. I didn't take that into account in any way, so that could be one of my mistakes. But yeah, let's look just right into the results. We can start the animation, and there we will see how it's gonna go for the left side. We can see the acceptance criteria here changing. Let's see, maybe for the Rhesus, we can decide if we want to have the acceptance criteria or the diagram zone. I will go for the diagram zone. And let's just shortly look here for the diagram zone. If the diagram zone gets red, then this hinge completely broke. If it's purple, then it's still in 20% or something of its capacity. Or 40. Not sure for the FEMA currently, for the steel. It's 20 for reinforced concrete at least. But yeah, so let's go for that and start it there. Now we see there it's red, there's the red, that's red, red, red. And that's the moment, the 0.38 or something was that. Well, we can also go here and see the overall UX deformation. Here what we see, the hinge is broken, this hinge is broken. Every hinge kind of in the system is broken. Am I right? Everything broke. Everything broke. Everything broke. Everything broke. Everything. Yeah, I'm right. Everything broke there. So that's where the system gets unstable for some solvers. That's that situation, 0.38, for example. But with this mix of solver, we can have it kind of moving free anyway and still capture the movement. So that's a benefit of that solver type. Well, and then it goes back. And it's gonna go, yeah. I think the figure explains itself at that place, and I don't really need to explain further. Exactly. Maybe for the cyclic behavior, we don't have direct cyclic behavior considerations there. So it's gonna be I don't know by heart. I think it's the normal kinematic one, or isotrope. I don't know it currently by heart. I will search for that afterwards. So it's also gonna, anyway, this cyclic behavior is one of our next topics, as well as the initial state topic. So it's gonna follow up. Okay, so that's the goal for, the investigation for our performance-based design. We can also look at, there we see a bit of our goal there. That should be our cyclic behavior, but you see it's not as I wish it to be yet. We can, in the end, we will have the backbone curve as well as the cyclic behavior within the diagram. That's the plan to go. What we see here is that the nonlinearity of the hinges is considered at that point, also with the maximum moment. For the hinges itself, the results can also be inspected within the results by member, the local plastic deformations, and there we have, if it's collapsed, what's the yielding moment in Y direction and Z direction, and so on. So here's all that information for each time step. Also the tables here change as soon as you change the time step. Okay. So, and that's it for this type of performance-based design. Now for the last topic, I think I will leave out how our auto tests work for it, because the time is running out. But at least I will be able to show you that this simple test for our reinforced concrete hinge. You just saw, let's go for the results first, because we can currently see the behavior of those hinges only by results. So we will go here. That's the backbone curve of our hinge. We have a reinforced concrete beam here. I made the analysis kind of, I made it as prescribed nodal deformation, so deformation controlled, and I also made it force controlled. But what's this one? It's the force controlled one, but it's also working because I have a nice system for it. Let's say it this way. Here at the bottom, there's the hinge. We also have two supports here, so it will be stable even though it goes further than this point. That's how our solver would say it's gonna be unstable. Sorry. Now, what we do here, we will increase the loading on this loading. Okay, wait 1 second. I need to change it for the horizontal load. We have the load on top. So it's going to rotate and it will cause a moment at the bottom here. And this will lead us to this graph of this hinge. And this hinge, as you can see, the MY, it's about 30 kilonewton per 30 kilonewton. It will be shifted at 0.005 rad. So 0.005, we will remember that. There it loses its strength to 20%, and we will also remember the 0.01 rad. There it loses it completely. So now let's go into this table. That's at the bottom there's some automatic testing, so I tested it for different scenarios. And on the top right side we see this table for that specific test. We were in the last row here, so we see the A value, which is 0.005 rad. So the A value gives the plastic deformation until it gets to 20% residual strength. And we see the B value, which is 0.01, and we also confirmed that inside the program. Well, as you can see here, the hinge, let's go for that again. The hinge is just placed pretty simple. We're gonna go for hinges. I'm just gonna pretend that I'm gonna create a new one. Okay, but one important stuff for now, maybe this here should be fixed. But I think this is already, it was a bug, but it's already fixed as far as I remember. So this shouldn't change anything anymore. But it was previously, it only works if this here is fixed and then you select the ASCII one. So you select this ASCII 4170 hinge within this nonlinearity, and then you have some information, but not really a lot of information, since the information is only gotten after calculation. That's why all of that information will be in the tables. It's not there yet. Currently, the only way to investigate on those hinge results is via those calculation diagrams. Okay, so that's how you set it. One more thing is, it's working for multiple materials. So in this case, we used the ASCE standard. Let's go for based at a concrete design. You will always need to have the concrete design add-on active and either the time history or pushover analysis add-on active. These are the requirements for those hinges. And for them to work, the material need to be, well, they need to match the concrete design standards. So you can't combine like Eurocode material with ASCE standards, because the yielding moment will be calculated from, well, it needs to match. It's the same as the material needs to match the concrete design add-on in the concrete design add-on itself. So the next thing is what material value is used. We see here the material values for ASCE is FC bar. We have this 20.684. You can also make it user-defined and change it there. I think there's no estimated values there yet, so this value is the one that is used. For Eurocode material, that's a bit different. It's gonna use the mean value, because it's the European estimated value, kind of. Even though the formula is quite awkward, it's just 30 plus 8. So if it's really the estimated value, I adopt it, but yeah. I'm just not knowledge enough to well say that, to be honest. Okay, but anyway, here for the hinges, the FCM is used and not the FCK. So the general rule is if there's a mean or estimated value, it should use it. If there's none of that, it will just use the standard value. Okay, and that's about it. Then maybe one more thing, even though we are a bit over time, I'm sorry for that. Let's go for our automatic test. That's something different, because those hinges are special on, well, on their behavior. There's always, as you can see, I did several load combinations. The difference is I changed the shear force, and the shear force for the first one is, for example, 308. For the second one, it's gonna be 99. For the third one, it's gonna be 148, and so on. So this test investigates on different shear forces for the hinge. And I selected, this is kind of part of our automatic test system also. Well, it's a bit more complex than our automatic test system, because in the automatic test system, it is even reduced in the calculation. Within here, we just calculated like some points on the most top part. Then you see here 0.005 to 0.01, it drops to this 20% residual strength. And at this 0.01 to this a bit higher, it will drop to 0. That's what's tested here, like this RUT values. And if we go for the table of our presentation, that's here on the bottom. So we see I used it with the CO5, 6, 7, and 4, all with different shear values, and it's matching our rotations are matching our A and B values. That means those hinges work shear dependent in the program, which is also given here under point D. V is the design shear force from NSP, so for pushover or time history. It uses the actual shear force for its behavior. That means the hinge behavior also is iterative, which is kind of one more non-linearity and makes it quite complex. But it's working. That's quite cool. And yeah, let's go for the last thing, and that are just some tips for the nonlinear time history. One thing is the nonlinear solver is kind of gifted for the time history add-on. No additional purchase is needed. Everyone who has the add-on already can just use it, so feel free to try it. Then we have a warning implemented if something is not within our automatic tests. So as soon as the warning is there, just use it with caution and use your engineering judgment. Then, the big benefit is we didn't want to block any feature, so everything is possible, even though it is not recommended for all combinations, to be honest. So that's the next tip from myself. It's something I call the Bausteinprinzip, modular principle in here for the validation, because in Rfem 5 I got lots of customer models which just had tons of non-linearities mixed, and they just said it's not converging. Yeah, that's quite hard to investigate where's the problem with that. So please insert one non-linearity or one problem after each other and investigate on its plausibility. Because else how you just stuck with tons of calculation time or convergence issues, and it's gonna take more time than like building it up like that. Then the Rayleigh damping can be defined with the first natural frequencies from the modal analysis. That's a bit better defined in the linear time history webinar for bridges. For nonlinear, you should account also for like stiffness reductions and so on with the modal analysis structure modification. You can do that. And currently, the beta damping can lead to convergence issues. So if that's a problem in your model, try also run it once without beta damping. And that could help on investigating on the results and then adjust the beta damping or time steps or whatsoever. So, and that's all from my side. Thank you for staying a bit longer than the normal time, but I think it was quite some stuff to show you, and well, I think it was a cool webinar. It was a cool first webinar of the year, and this analysis type really makes fun for me. I hope it will for you too, and I wish you a really great start into the year, and I hope this bang did help a bit. So have a nice year. Bye-bye.
Thank you, Thomas, for your presentation. At the end, I would like to introduce our online courses. For example, the Rfem 6 course. It's a course for beginners. Then the Eurocode 2 course for the reinforced concrete design with Rfem 6. Then the Eurocode 3 course for the steel design. Eurocode 5 course for the timber design. And Eurocode 8 course for the earthquake design. You can get more information when you scan the QR codes or click at the links on our that leads to our website, and you will get more information, also the prices. You can get such a course for free when you submit a customer project. You can scan the QR code or press that link here. Then you can download your files. You can also write me an email and I will write you back what I need for publishing the customer project. It's not much work for you, and you will get such a course for free. You can get more information on our website, dlubal.com. For example, you can find the knowledge base articles. You can ask our AI assistant, Mia, all the day and all the night, 24/7. Just try it. And you can also find the recorded webinars. In the next days, you will get an email with a link to the page where you can find the recording of this webinar and the files and the slides and so on. Okay, that's also all from my side. I thank you for your attention. Thanks to Thomas for the presentation. Thank you, Victor, for your help by answering the questions. I wish you all a nice rest of the day. I hope we meet each other in a future webinar. See you. Bye-bye.